I already stopped the other video, and I probably could and should splice this onto the end of it, but too late. I just didn't have enough of an idea of where I was to think about it. I apologize. We said if you have a benzylic lone pair, those groups are activating. What do you think all these have in common? Benzylic lone pair. If you have a plain carbon, AR is a benzene. This is a pi bond thing. Plain carbon, donors. Everything on this part of the table are electron donating groups. They are all activators. But some of them are stronger activators than others. The things that have the benzylic lone pair, stronger activating than the plain carbons down here. Everything that's activating, though, is orthopara-directing. So this is regular benzene, and all of those groups make walens that are more stable than benzene's walens. Yeah. Can I ask you groups that are not on this list and expect you to answer them? Yeah. Will I ask you groups that are not on this list and expect you to answer them? Yeah. All right, let's continue on our journey. I'm going to avoid drawing the formation of electrophile because all these reactions that we've drawn are nitration. Why are we drawing nitration? Well, we're drawing that one again and again, not so that we can draw only one type, but because these all undergo electrophilic aromatic substitution, the same summaries that we're making for nitration could be made for halogenation, alkylation, acylation, what am I forgetting? Sulfonic acid, sulfonation. Yeah, we've only drawn nitration, but it's electrophilic aromatic substitution that we're really discussing here. We continue. I really wish I had just a tiny bit more real estate on these slides, just a tiny bit more. I wish I drew just a tiny bit smaller. We're going to draw ortho and meta. Let's avoid para this time because we know that para does the same that ortho and meta do. So if we add this meta, at least if you're not drawing along with me, you should be, but at least if you're not, be ready to answer the question, is any better than any other? Who's the winner, chicken dinner? Which should be my product. All right, and I'm skipping the some base somewhere comes to clean up. All right. There's ortho, there's meta. Para would look a heck of a lot like ortho. Nitration of benzonitrile. Those are my three possible products. Here's my actual observed percentages. This one makes meta as the major. That must mean there's something special about the meta walens back here. Well, I don't immediately see anything special about meta walens. They're all secondary carbocations in ortho and meta. Oh wait, actually, this one is a tertiary carbocation, but that's actually worse. What? Resonance to the rescue. It's all about resonance. If I draw this resonance picture, where I flip electrons from the carbon triple bond out toward the nitrogen. The nitrogen has had one lone pair all along that we just didn't draw. But if I flip electrons toward him, I messed up somewhere. These pi bonds in this last structure are in the wrong place. I apologize. It happens to students all the time. I'm leaving this in. I'm not editing it out because I want you to see that I make boo-boos too. Lots of you like to, should draw pi bond curved arrows. The truth is I don't require curved arrows for resonance, but I do require curved arrows for all mechanism stuff otherwise. But if it's helpful to you to draw curved arrows of mechanisms, sure, do it. My bad, I apologize, but I got it remedied now in my original purple, but I did not fix it up here so far. Okay, no wonder. All right, so if I fold electrons from that triple bond out toward that nitrogen, you say, why would you do that? That is not helpful at all. It's not helpful except that, oh man, that's real bad. What's so real bad about that? I've got a positive right next door to another positive. That is terrible. Terrible. Awful. No good. Very bad. Oh, that's real bad. Oh, actually, I'm so distracted by my other mistake, I just made another one. That nitrogen is negatively charged. Ugh. So these positives right next to positives, really a bad sign. Not good at all. This red resonance structure, we would normally say contributes negatively to the hybrid. So we don't normally draw a resonance structure like this. Then why the heck did I do it? Because sometimes groups can donate by resonance, and sometimes they withdraw by resonance. And this is actually a sign of cyanide withdrawing by resonance. This group is not a donor, it's an electron withdrawing group. And that red structure shows me how that can withdraw. Two positives next to positives, really, really bad. So even if I didn't draw this red structure that contributes negatively to the hybrid, we know that this carbon has a partial positive on it anyway because it's connected to this very electronegative nitrogen. So even if I didn't draw this, partial positive exists there, so a partial positive right next door to another positive, not a good sign. So ortho is bad. Para is also bad. And meta, it's not that any of the Weylands are any better than any other in meta. It's just that it's not as bad as ortho and para. In meta, it's just not terrible. So that's why meta is what forms here. We made meta because we would say this blue circled thing is an electron withdrawing group. It's a deactivator. What does it mean to be a deactivator? It means reacts slower than benzene, and it's a meta director. It's not that meta is any better than any other. It's just not as bad as ortho and para's Weyland resonance. Okay. So we said there are 4 situations that you might find yourself in the benzylic spot. I left out the C. In the benzylic spot, you might have a lone pair. That lone pair will donate by resonance. In the benzylic spot, you might have a plain carbon. That plain carbon will donate by hyperconjugation. In the benzylic spot, you might have a partial positive, like nitrile had a partial positive. That's a withdrawer that might withdraw by resonance. It might withdraw by induction. It just kind of depends on specifically which kind of group it is. And if you have a legit positive, that's a withdrawer. Again, maybe by resonance, maybe by induction. It just kind of depends on which group you have. Partial positive is less of a withdrawer than a legit positive. I think that makes sense to you. Partial positive. Oh, look. Partial positive. Oh, look. partial positive. I'm drawing resonance arrows over here. Oh, look, partial positive. Oh, look, partial positive. Oh, look, partial positive. Oh, look, partial positive. Sulfur. Oh, look, partial positive. Those things, partial positives. These down here, legit, 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 legit. Too legit, too quick. Hey, hey. Yeah, that nitro, partial, legit positive. So, yeah, some of these that had partial positive are considered strongly deactivating. We'll talk some more about that. But these things with partial positives are moderately deactivating. They are all meta-directing. Okay, this is the second half of the table that we saw at the very beginning of this video. And this purplish color says these are ortho-para-directing. The halogens are super weird things. The halogens are super weird electrophilic aromatic substitution things. Because the halogens have a lone pair in the benzylic position, so they want to donate by resonance, but they're also very electronegative, so they want to withdraw by induction. So the halogens are a conundrum. What that means is they're deactivating because they react slower than normal benzene, because they're electronegative. But they have that lone pair that can give us the extra resonance picture, making ortho and para more stable than meta, so that's why they're still ortho-para directing. The halogens are deactivators, yet ortho-para directors. They're electron groups, donation by resonance, withdrawal by induction. They're electron groups. They're deactivators. They are ortho-para directors. Yep. Let's see if we understand the take-home messages. All meta-directors are deactivators. True story. All ortho-para directors are activators. False. That's true except for the halogens. All ortho-para directors are activators except for the halogens. Plain carbon groups are activators. Yeah. If an atom with an unshared pair is directly attached to the ring, it's an ortho-para director. Yeah, that's situation number one, lone pair. Electronegative groups with no unshared pairs are meta-directors because they have a partial positive. Yeah. Why are the halogens ortho-para directors and deactivators? Well, I wrote this down as a question for us to discuss, but actually we just spent a minute discussing them. They're a conundrum because they have a lone pair that wants to donate by resonance, leading to ortho-para, yet they're electronegative, so they make benzene react slower when they're on benzene. They react slower than normal benzene would have. Yep. Why is, for example, NH2 a better activator than that other thing? Why is NH2 a better activator than this thing? Well, both of these things have a benzylic lone pair, leading me to say both of them are donors, both of them are activators, but my question actually said they're activators. But why is NH2 a better activator than that other group? This is aniline. This is acetanilide. You don't have to know that, but it's easier for me to refer to them by name sometimes. Why is aniline a better activator than acetanilide? It's got to do with distractions. It's a lot easier to learn organic when you don't have distractions around, right? This lone pair can donate to the benzene, but it's also distracted by that COO up there. Oh, we attached to the wrong carbon. We almost attached to the wrong carbon. So that lone pair, can donate to the benzene, but it could also be delocalized this direction. This lone pair is solely focused on donating to that ring. This lone pair makes this benzene electron rich. It's got tons of electron density. Bring on the electrophiles. It's really ready to react. This lone pair can donate to that benzene. It's also got tons of electron density, really ready to react, but it doesn't have as much electron density because that lone pair is not laser beam focused. It's distracted by this other carbonyl group over there. Yeah? Okay. Why is, for example, NH2 a better activator than OH? Well, that's also about resonance. Let's actually put on an electrophile here in the para spot. That's not very legible down there, but there's an electrophile. It's just an E down there in a para spot. That gives me those two valence. If I draw the resonance of those two valence, one of the resonances of those two valence, I get this. There are more resonances, but I'm stopping there. And I get this. Again, there are more resonances, but I'm stopping there. Because that's enough to answer my question. Why is NH2 a better activator than OH? It has to do with these two resonance structures. If you compare those two, which one is better? Both of them have everybody with an octet, but nitrogen is less electronegative than oxygen. So nitrogen can handle the positive better than oxygen can. So this one is better, more stable than that one. So because of that, NH2 is a better activator. Less electronegative means better at donating, right? Less selfish. Okay. You will be asked to explain why one thing is ortho, meta, para, director. Why? And why usually means drawing resonance. You must be able to explain relative order, like those two questions we just asked about. Why is this more than that? Why is this more than that? Yeah, you must be able to explain why. I will ask you about groups that are not found on table 18.1. Be prepared to discuss. What's the general principles? You might find yourself in 4 situations. A benzylic lone pair, a plain carbon, a partial positive, a legit positive. That 4 summaried thing tells you all that you need to know about donors, withdrawers, activators, deactivators, ortho, para, meta, directors, etc. Yeah. Okie doke. When you're presented with a problem like this, where the heck do you start? Well, the first question is, I've got 2 benzenes. Which benzene should add my nitro group? HNO3 and H2SO4, I'm adding a nitro. Does the nitro get added to the red benzene or the blue benzene? Well, it all depends on what's connected. The blue benzene has this thing connected, and is that thing considered an electron donor or an electron withdrawer? It's an electron donor. Why is it a donor? Because there's a benzylic lone pair. Benzylic lone pair, electron donating group, that means it's an activator. That means it's an ortho para director. Yep. The red benzene has this group connected in its benzylic spot. This group is an electron donor, electron withdrawer. Electron withdrawer. Why is it a withdrawer? Because it's got a partial positive in that benzylic spot because of that resonance that I drew up there. That means it's a deactivator. That means it's a meta director. So what that tells me is red benzene has less electron density than a normal benzene because it has a deactivator. Blue benzene has more electron density than a normal benzene because it has an activator. So I'm going to add it to the blue, not the red. Yeah? And then, based on steric bulk, I'm going to actually predict that this is my only product formed, because it would actually be pretty difficult to get a nitro into the ortho spot here or here. It's a trigonal planar, all these benzene things. We haven't talked any stereochemistry. Oh, isn't that nice? We haven't talked any stereochemistry about this benzene stuff because it's trigonal planar. You can spin around this single bond right there, and it doesn't really matter which side is ortho. Yeah. But I'm going to predict that's my one and only product because of steric stuff and the ortho just being too crowded. If you put ortho, I wouldn't mark it wrong, but para should definitely be major here because that stuff is big. All right, let's do some more. This time, we're not going to talk about two benzenes because we don't have two different benzenes, but we've got two different functional groups, two different groups on my thing. Red circle group is electron donor. It's an activator. It's an ortho pair director. You should hopefully be able to rattle this off as quickly as I'm rattling this off, or at least soon you are. Ortho to him is here, here, and pair to him is there. Alrighty. Blue circle group is the same group. It's an electron donor. It's an activator. It's an ortho pair director. Ortho to him is here, here, and there. Oh, look, they agree. But the problem is they agree on 3 positions, and we probably want to put on one group. We're not going to do multiple substitutions yet. We will talk about them, I promise. But we're going to put on one group. Do you think it's likely that our one group will squeeze right between those 2 carbons right there? Not so much. Sterics would not favor that. And then whether it goes on this carbon, or that carbon, the ones that now have the purple arrows, as soon as I get rid of that one, whether it goes on this carbon or that carbon, it doesn't matter. Again, it's trigonal planar, so they are equivalent carbons. So let's put it on that one up there. What am I putting on there? It's not a nitro this time. It's an acyl group. That acyl group. So I've got metaxylene. I started with metaxylene, and I added an acyl group next door to one of them. Okay. Blue circle group. Blue circle group, I'm looking at that benzylic position. At that benzylic position, I have a lone pair, plain carbon, partial positive, legit positive. I have a partial positive. That means it's a withdrawer. That means it's a deactivator. That means it's a meta director. Meta to him is occupied and here. All right. Here, I'm looking at that benzylic spot. Oh, look, it's the exact same group attached in the exact same way. It's a partial positive. It's a withdrawer. It's a deactivator. It's a meta. Meta to him is occupied and here. Oh, excellent news. They agree, and they agree on one position that is unoccupied. And what am I putting in that one position that is unoccupied? A nitro. NO2. Yep. Blue circle group. That's got a benzylic lone pair. Lone pair, that's what that stands for. It's an electron donating group. It's an activator. It's an ortho pair director. Ortho to him is here, here, and occupied. Red circled group. It has a benzylic lone pair, but it's also a halogen, so it causes some confusion. It's a deactivator, yet orthopara. Halogens are weirdos, I know. Ortho to him is here, here, and occupied. Uh-oh. In the others, they agreed. We had to choose steric stuff, but in the others, they just automatically agreed. They don't agree here. We have to reach some sort of consensus when there's a tug of war going on between these two groups. It's all about who's better at their job, who's the better activator, who's going to make this benzene electron-rich oxygen of phenol. So let's obey oxygen because he's the one that's more likely, he's the one that's making this benzene activated, and the more activated it is, the faster it will attack an electrophile. So we're going to obey the oxygen. And what are we putting? We're putting a bromine there. If you are not napping, you might have noticed that this is Br2, just Br2 with no fever. There's no Lewis acid catalyst here. Yeah, we've got a little bit more to say about that, but phenol is so activated. How activated is it? It's so activated that you can put a halogen on even when you don't have that strong Lewis acid catalyst. We've got more to say about it, but phenol is super activated. Okay, next. Well, we add Br2 and fever to benzene. Let's add a Br. There's nothing dictating where that Br has to go. Add fuming sulfuric acid to benzene. There's nothing dictating where that sulfuric acid has to go. So put a sulfonic acid on. But now there is a group on your benzene in each of these, and you have to decide where your next stuff goes. So up here, I have a halogen. Halogens are weird. They're kind of like they're kind of like donors. They're kind of like withdrawers. They are definitely deactivators. They are ortho-para-directors. So that means I get a sulfonic acid para for sure, and probably some ortho as well. But remember, I said we're gonna often. I can't squeeze this. Oh boy. We're often gonna ignore the ortho and get only para. We'll talk a little bit more about it as we go along. I promise we will. Here, I've got a sulfonic acid. Sulfonic acid has a partial positive. Partial positive means electron withdrawer. Electron withdrawer means deactivator. Meta. So the order of addition, oh man, it's a super big deal in these reactions, these benzene reactions. When I did bromination followed by sulfonation, I made ortho and para. When I did sulfonation followed by bromination, I made meta. The order of addition is super important. What that translates to is synthesis stuff. As we are about to move into a bunch of synthesis examples, the order of addition is super important. But I have this mantra where I say, even if you suck at regular synthesis, and students often feel very hesitant about synthesis, they're very not confident about synthesis. Even if you suck at synthesis, in general, students can do electrophilic aromatic substitution synthesis. I believe in you. One more example before we move on to the synthesis stuff. If I add nitric acid, sulfuric acid to this thing, this is an electron donating group because it donates by hyperconjugation, because it's a plain carbon, it's an activator, it's an ortho-para-director. Because it's kind of bulky, I'm going to put my nitro in my para position only. All right. What if I do sulfonation? This is sulfonation. You knew that, yes? Well, exact same rules apply because it's the same reactant. So let's put that sulfonic acid in the para position. Then what if I do nitration? All right. This guy says, I like stuff ortho to me, and para is already occupied. This guy is a meta-director, and meta to him is here or here. So they agree, and because it's a benzene trigonal planar thing, doesn't matter which side you add it to. Let's add a nitro over here. Sulfonic acid. Do you remember that sulfonic acids were special? When we blew through those 5 electrophilic aromatic substitution reactions so quickly, there was something special about sulfonic acids. They can be put on like so. You can add superheated steam to take them away. So superheated steam, that's really acid water heat mostly. Acid water heat. That's taking away the sulfonic acid, desulfonation. So this is a lovely slide that says, I've got a big bulky thing here that's an ortho-para-director. So when I try to add a group, it goes para. But what if I definitely wanted it to go ortho? Like what if I wanted to force it to go ortho and not get any para product? You go through this route instead. Sure, it's a longer route, but it efficiently makes ortho and only ortho. Over here, if you got any ortho, it's a minor product, like little baby minor. But over here, it's the major product, aka the only product, because you went through so many steps to get there. This strategy is called protecting group chemistry. We're going to talk several times about protecting groups, but what happened was the sulfonic acid here is a protecting group because if you tried to directly nitrate, the nitration would go on the para. But you sulfonate to protect that para spot from reacting, to occupy that para spot temporarily. Then you put on your nitro group. Then you take off your protecting group. So protecting group chemistry, put your group on to protect what you don't want to happen. Do the reaction as you wanted it to go in the first place, and then take that protecting group off. We're going to do several things with protecting group chemistry, but that's enough for this video. We're going to do synthesis after synthesis after synthesis in the next one. Be prepared.